Hey guys, welcome to A level chemistry and physics, and this time we're going to cover AS level radioactivity and the discovery of atoms. This video will assume you've seen the previous video of particle physics and will use some of its knowledge. So, in case you haven't checked that video out already, do go and see the whole video because that knowledge will be essential to this one. Alright. In this video, we will cover how the structure of the atom was discovered, who put it forward, and how does radioactive decay occur. So, understanding the atom over the years, throughout history, there has been a constant attempt to understand what is the most fundamental building block of the universe. It started with Greek philosophers like Aristotle. Aristotle first put forward the idea that everything was made of the four elements: earth, fire, water, and air. Then there was Democritus who first put forward the idea of atoms. He said there has to be something which, when you keep dividing something into two and further, that becomes indivisible. He coined this indivisible building block, atoms. Then came along J.J. Thomson very recently, I think in 1930 or so. He used a cathode ray oscilloscope to put forward his ideas about a plum pudding model, where there was in the center a positively charged plum surrounded by a negatively charged pudding. But the most important and revolutionary experiment was conducted by Ernest Rutherford, which was called either the alpha scattering or the gold foil experiment, which gave the scientific community the most accurate idea of what the atom was made up of. The gold foil experiment is crucial to the AS level syllabus and one that we will examine. This was the setup. So on the left, you have the source of alpha particles. The symbol stands for alpha. So we will cover what alpha particles are later on, but for the purpose of this experiment, alpha particles are just positively charged particles. And then in front of the source, you will have a thin gold foil, which is approximately like 9 nanometers thin or something. So it is like really, really thin, almost the size of um, the thickness of one or few atoms or so, so like really thin, and it was surrounded by a circular fluorescent screen. This screen was put to detect the deflection or detect any positively charged particles that would strike it. So the source was switched on, and alpha particles that were made to pass through this thin gold foil, and we were to examine whether what would happen to the alpha particles if they would pass straight through, get deviated, so on and so forth. So I've broken down this experiment into observations and conclusions. We will examine three of each. So what were the observations? The first observation was that most of these alpha particles passed straight through undeflected. So that was most of the particles were found right behind the gold foil, as if they went straight through, perfectly in line with this perfectly straight through the gold foil and were found right behind it, completely undeviated. They were unaffected by the presence of the gold foil. Some alpha particles are deflected by a very small angle, about 45 to 60 degrees or so. So they're deflected by a very small angle, or deviated by a very small angle, if I were to say, and was still found behind the gold foil. The third observation was that some alpha particles were completely deflected from their path, greater than 90 degrees. So it was as if they had struck against something and completely bounced against it, and therefore they were found in front of the foil instead of the other alpha particles that were found behind the gold foil. What are the conclusions we can draw? So, by the first observation, where most of the alpha particles pass straight through, we can draw the conclusion that atoms are mostly empty space. The only way the alpha particles passed straight through was because they had nothing that came in their way. Passing straight through meant there was no obstruction, and therefore atoms had to be mostly empty space for alpha particles to pass through completely unaffected. Number two, the center of the atom is positively charged. I said before that alpha particles are positively charged particles. When they were deviated by a small angle, it had to be an electrostatic force that was repelling them. Only a positive charge can repel a positive charge. Therefore, the atom's center had to be a positively charged particle for it to repel the alpha particles. Therefore, the second conclusion is that the center of the atom is positively charged. The third conclusion is that the center of the atom is very hard and dense. For the particles to bounce back completely off their course, there had to be something very hard, strong, and rigid, centered in its position, which the alpha particles bounced against. Therefore, the center of the atom must be very hard and dense. So this gave us a very convincing image of what the atom was. Through previous experiments, we knew the existence of electrons. So there were definitely electrons in there with a positively charged center, and center was much smaller as compared to the rest of the atom. With all these ideas, all these observations and conclusions, Ernest Rutherford put forward a convincing model of the atom that the entire scientific community accepted. This experiment was pivotal in understanding the subatomic structure, and it is the reason why we still study this experiment today. Right, now let's get to radioactivity. The first thing we have to cover in radioactivity is isotopes. So this is most probably a topic covered in your previous classes, but for the sake of this video, we will still go through it one brief time. Isotopes are just atoms of the same element with the same proton number but different nucleon number due to difference in neutrons. One of the examples is hydrogen, the hydrogen's most common isotope is hydrogen 1, which when it has one proton and one electron in orbit. However, it has two other isotopes, deuterium and tritium. Deuterium has one proton, one neutron, and one electron. Tritium has one proton, two neutrons, and one electron. So the most common hydrogen isotope has zero neutrons, deuterium has one neutron, and tritium has two neutrons. Other elements with more than one isotope include carbon and chlorine. There are more elements with more isotopes, but this is just one of the two of the most common elements with more than one isotope. So isotopes are radioactivity. Only some isotopes of certain elements are radioactive. I believe tritium, hydrogen's third isotope, is radioactive, and carbon 14 is also radioactive. So what do you mean by radioactive? Radioactivity is defined as the emission of ionizing radiation or the emission of particles that is caused by the disintegration of atomic nuclei. So this happens when one nucleus breaks down into another nucleus with the release of energy. That is what radioactivity means. For example, carbon 14, which is the isotope of carbon with 14 nucleons, is radioactive. It decays over time to form other elements. These isotopes that are radioactive in nature are also known as radioisotopes. And do note, not all isotopes are radioactive. Only selected few of them are radioactive and are known as radioisotopes. The isotopes commonly used in nuclear reactors, for example, include uranium-238 and plutonium-239. So this graph, what is this graph about? So one thing to notice is this graph has the number of neutrons on the y-axis and the atomic number or the number of protons on the x-axis. This line you see over here is known as the line of stability. That is, on this line, the number of protons is equal to the number of neutrons. However, these points which are plotted next to this line are the points of actual elements in the periodic table or actual elements and isotopes of the periodic table. So initially you see that the number of protons are roughly equal to the number of neutrons because these isotopes are close to the line. However, as we keep going along the x-axis, the number of protons increase exponentially or at a very high rate. So if we take uranium-238 for example, it has a proton number of 92, which is roughly here. When you see the number of corresponding neutrons, it is so high it all actually goes off the charts, 146 or so. So because of this large difference between the number of neutrons and number of protons, the uranium core becomes unstable and prone to decay. So why is it that the nucleus The nuclei with a high number of protons tend to have a disproportionately high number of neutrons. By disproportionately, I mean much, much higher than the number of protons. We know by definition that protons are positively charged, right? When there are too many of those protons in the nucleus, they start to repel each other due to the electrostatic force of repulsion. Like repels like, right? So positive will repel positive. It becomes harder and harder for the strong nuclear force to hold the nucleus together, and therefore neutrons are used to increase the distance between the protons and prevent them from repelling each other too strongly. However, when there are too many nucleons, that means too many neutrons and protons, the nucleus, due to increased mass, itself becomes unstable and decays. Radioactive decay. Now, finally, we come down to the types of radioactive decay. There are three kinds of radioactive decay: alpha, beta, and gamma decay. However, there are three rules which hold true for all decay processes. That is, the nucleon number, proton number, and mass energy is conserved. What is mass energy? Well, we will cover that later on in the presentation. So, what is alpha decay? Or firstly, what is an alpha particle? An alpha particle is essentially the nucleus of a helium atom. It has two protons and two neutrons, giving it a total of four nucleons and an overall charge of 2 plus. You can see the symbol over here for alpha with 4 and 2. Note, quick note that when you use helium as the symbol, you have to put the 2 plus charge. However, when you use the alpha symbol, which is on the right, it is assumed that the particle has a 2 plus charge. And these are both correct ways of representing the alpha particle. It is up to you which one you want to use. So alpha decay occurs when an unstable nucleus decays to form another element, as well as the release of alpha particles in the process. For example, we have an element here with the nucleon number 222, proton number 88, which decays to release alpha particles, and another element with 218 nucleons and 86 proton number. Do note that the rules hold true over here. There are 222 nucleons on the left, and there are a total of 222 nucleons on the right. That is 218 plus 4. The same holds true for proton number. 88 on the left and 2 plus 86, which equals 88 on the right. Beta decay. So what are beta particles? Beta particles are essentially a beam of electrons. They have negligible mass and a charge of -1. But we also need to take into account their antiparticles, which are beta plus particles. They have a negligible mass and a charge of +1. Both of these are important because they have the respective types of decay which we will examine. So there are two types of beta decay, beta minus and beta plus. Right, so what is beta minus decay? In beta minus decay, an atom releases beta particles and the proton number of the element increases by 1. And another particle known as an antineutrino is released as well. We'll come to antineutrinos and neutrinos a little later. So in this example, you see carbon 14, which has a proton number of 6 and a proton 14 nucleons. When it decays through beta minus decay, it forms nitrogen, 14 and 14 nucleons, 7 protons, with the emission of beta particles or electrons, as you can see, and an antineutrino. So what do you mean with the proton number goes up by 1? On the left, on the right, and on the right, both the nuclei have 14 nucleons, right? So the nucleon number is constant. However, carbon has 6 protons, whereas nitrogen has 7. So for the nucleon number to be the same for both nuclei, but the proton number to increase, one neutron has to convert itself into a proton. Therefore, we can say that beta minus decay is essentially the conversion of a neutron into a proton. As can be seen by this equation, where a neutron with zero charge and one mass gets converted into a proton with one mass and one positive charge, with the release of the release of beta minus particles and an antineutrino. The question is, what are antineutrinos and how are they discovered? So antineutrinos and neutrinos, they're a particle-antiparticle pair. They have a zero mass and zero charge. So how did we detect them? What happened was when the beta decay was being studied, it was noticed that the beta particles have a range of speeds. That means some were slower and some were faster. So the fact that all of them were not the same speed, that means some of the momentum they had was being lost or being absorbed by another particle. Therefore, it was theorized that there is some other particle that is carrying the rest of the momentum, which is slowing the other beta particles. This particle came to be known as the neutrino or and the antineutrino, which were discovered in 1956. Beta plus decay is essentially the opposite of beta minus decay. An atom releases beta particles, but in this case, positrons or positively charged electrons, and the proton number of the element decreases by one. And also, contrary to beta minus decay, a neutrino is released in this case. In beta minus decay, antineutrinos were released, but in beta plus decay, neutrinos are released. So there we have a carbon atom on the left with 11 nucleons and 6 protons. This atom I do not believe exists. This is just for the sake of example. So there's 11 nucleons, 6 protons, releases a boron atom of 11 nucleons, 5 protons with the positron and the electron neutrino. Do note that both the nucleons are conserved and the protons are conserved on both sides. That means 11, 11, and 6 on the left and 5 plus 1 on the right. Beta plus decay is essentially the conversion of a proton into a neutron, just the opposite of beta negative decay. This again because the nucleon number is the same for both the nuclei that are formed, 11 and 11, but the proton number decreases. For that to happen, a proton has to convert itself into a neutron. Therefore, beta plus decay can essentially be boiled down to this equation, where there is a proton with one mass, one charge converting to a neutron with one mass, zero charge, and a beta plus particle with a neutrino. This is where particle physics comes into the picture. So we notice that both kinds of beta decay involve the conversion of one hadron to another, either a proton to neutron or vice versa. We talked about how similar the protons and neutrons were in our previous video, that the proton was an up-up-down quark combination, the neutrons were an up-down-down quark combination. So there is only a difference of one quark between them. When both kinds of beta decay occur, we can safely say that two quarks do not change at all, and there's only one quark that changes itself from either an up quark to a down quark or vice versa throughout the decay process. The entirety of beta decay can be boiled down to the conversion of one quark into another quark. This can be seen in this diagram. So in beta plus decay, we see that there is an up quark that is converting itself to a down quark with the release of a positron and a neutrino. In the diagram, we see that there is an up-up-down quark or up-up-down quark, which is a proton in this case on the left, converting to an up-down-down quark combination, which is a neutron with the emission of a positron and a neutrino. So there is a up quark and down quark pair which remains relatively constant. These two. This is the same on both sides. It is only this up quark that converts itself into this down quark, while the other two remain constant. So the beta decay is essentially this up quark converting itself to this down quark. This is the opposite for beta negative decay. Again, this up and down quark pair remains constant, but this down quark changes itself to an up quark right here with the emission of beta negative particles and an antineutrino. Gamma decay is probably the most simple decay of all. It usually occurs in conjunction with alpha and beta decay and is only the emission of excess energy from unstable or excited nuclei. So there is you have an iodine nucleus on the left, which is and the star indicates an excited state or an excess of energy. On the right, it emits a gamma photon or gamma particle alongside a stabilized iodine nucleus. Gamma particles have no charge and no mass. They're essentially just photons, which is a fundamental particle and a bunch of energy. Therefore, on both sides, there is absolutely no change in the nucleon number or the proton number on either sides of the nucleus. So we come back to mass energy. I talked about how mass energy is conserved during the nuclear reactions. In most reactions, as we studied from before, it is only mass that is conserved. In nuclear decay reactions, however, it was observed that mass at the end of the decay was slightly lesser than the mass at the beginning. So where did the excess mass go? This was because the mass that was lost was instead converted into the energy, which obeys the law E is equal to mc square, which is the most probably the most famous equation in all of science. So due to the presence of this equation, there was a mass defect, or the mass was lost and converted into energy throughout the decay process. Therefore, we can't say that it was mass that is conserved throughout the decay process because evidently it was not. Instead, mass and energy in conjunction are conserved throughout the decay process. This single quantity of mass and energy came to be known quite self explanatorily as mass energy. This table is very important. Due to the restrictions of the keyboard, I decided to put a table instead which showcase the type of radiation and the types of symbols that are used. Do note that the beta particles have various symbols, and all of these are fine if you use them throughout AS level questions and so on. So that's it for today, guys. I hope you should note this table down. It is very important. And I will be covering the properties of each of these radiations in the next video. And if you have any doubts, please do not feel hesitant to mail me on the email ID I mentioned in the description. Thank you for watching.